Okay, hello everyone, and welcome to the second session of the ISRM Young Members Seminar Series. My name is Daisuke Fukuda. I and Ryota Hashimoto are the Young Members Group coordinators, representative of the Japanese Society for Rock Mechanics. It is a great pleasure for us to be here today. Thank you for attending this second session. Before starting, we would like to thank the support from International Society for Rock Mechanics and Rock Engineering, mainly of ISRM Young Member Committee, represented by Sehyeok Dakota. We also would like to thank to all youth representatives of national groups that have joined this initiative. Finally, we would like to thank Dr. Sho Ogata and Dr. Sehyeok Park for agreeing to present their works in this session. Okay, now we will take a few minutes to present key information about this seminar. This project attempts to promote youth community interested in rock mechanics, including engineers, research scientists, and students, to foster knowledge in rock mechanics among this community, to share experience both in the industry and the academia, and to strengthen relations between different countries. We would like to invite different young members to participate in this seminar series. The criteria for the speakers are: be an ISRM member and have a maximum age of 35 years or of 40 years if a PhD degree was obtained in the previous 5 years, and have worked in rock mechanics and rock engineering for a period no longer than 10 years. Speaker nominations can be made by the nominee's national group or by some other person or organization acquainted with the nominee's work. Self-nominations are also accepted. Nominations are to be addressed to the ISRM Young Members Seminar Series Organizing Committee. In the screen, you can see our contact email address. This webinar will be held every month. We invite you all to keep in touch. Okay, now I will hand over to the seminar of the day. Each presentation will last 20 minutes and will be followed by 10 minutes Q&A. For the smooth running of the seminar, so please turn off your camera and microphone during the presentation. If you have any questions after each presentation, you can use chat and also the raise hand feature in Zoom. Okay, let's move on. The first speaker is Dr. Sho Ogata. He is currently working as an assistant professor at the Division of Global Architecture, Graduate School of Engineering, Osaka University, Japan. Dr. Ogata holds a MSc in Civil and Environmental Engineering from Ehime University, Japan, and a PhD in Urban Management from Kyoto University, Japan. His research focuses mainly on the numerical modeling of coupled thermal, hydraulic, mechanical damage chemical process within fractured rock. Today, he will present a part of his research work on this topic. So, Dr. Ogata, the floor is yours.
Okay. Can you see my slide?
Yes.
Okay.
Yes.
Okay, go ahead. Thank you for kind introduction. Hello, participants. I'm so glad to give an opportunity to introduce my research work. In this presentation, I will present a multi-physics numerical model and simulation for predicting a series of rock permeability evolution process from fracturing to temporal sealing induced by geochemical creep. At first, I'd like to talk about research background. In order to examine the performance of the disposal facility of radioactive waste, evaluating the permeability of bedrocks that works as a natural barrier is very important. And it's well known that fracture generation during cavity excavation for disposal of radioactive waste has critical influence on the permeability change of bedrock. And in addition, after excavation, occurrence of geochemical reaction within generated fractures between mineral and groundwater may change permeability with time over the long duration. And this reaction depends on the coupled condition between temperature and stress and solid concentration and structure of rock fracture. Therefore, in order to examine the performance of a geological disposal facility of radioactive waste, we must develop a coupled thermal, hydraulics, mechanical, chemical model, namely coupled THMC model that can consider these influence of fracture generation. In other words, both fracture generation and subsequent occurrence of mineral reaction must be considered. Here, let me explain the process of particular interest in this study. It is a series of process from fracturing to subsequent occurrence of mineral reaction. Here, among mineral reaction, pressure solution is introduced. As shown in this figure, at first, fracture area is generated due to cracking. After that, when high compressive stress acts on rock, mineral dissolution occurs at asperity contact in rock fracture. And then fracture is gradually compacted by mineral dissolution with time. This phenomenon is pressure solution. When pressure solution occurs continuously, fracture aperture decreases with time as well as permeability. So, for accurately predicting a series of permeability evolution process during the geological disposal period of radioactive waste, a series of process from fracture generation to subsequent pressure solution within generated fractures should be modeled and incorporated into coupled THMC model. Previously, many coupled THMC models have been proposed. However, almost model can't comprehensively describe the coupled THMC process, including fracture generation. For example, recently, some models that can describe the coupled THM process, including fracture generation, were proposed. But occurrence of mineral reaction influenced by fracture generation wasn't considered. So, in this study, for predicting a series of permeability evolution process, we developed a new coupled THMC model that can consider both fracture generation and subsequent occurrence of mineral reaction, such as pressure solution, influenced by fracture generation. And then, by using the developed model, we conducted long-term prediction of rock permeability change within geological disposal facility of high-level radioactive waste. From following slide, some contents of this paper will be introduced. This work was performed with the Professor Hideaki Yasuhara and Naoki Kinoshita from Ehime University in Japan, and Professor Kiyosuke Kishida from Kyoto University in Japan. And this work won the Rock Mechanics Research Award 2021, presented by American Rock Mechanics Association Awards. If you are interested, please read this paper. Okay, I will explain the outline of the developed model. This figure represents the coupled interactions considered in developed model. As shown in this figure, this model considers coupled THMC interactions, including damage component. This damage component represents the influence of fracture generation. And these white arrows are interactions taking into account our previous model. And these gray arrows are interactions newly incorporated in this study. Among these interactions, especially describing the occurrence of mineral reaction influenced by fracture generation was most characteristic in developed model. This interaction is represented as arrows from damage component to chemical component. Okay, let's move on to the explanation of governing equation used in the model. In this study, isotropic damage model is used for calculating fracture initiation and propagation. In this damage model, the tensile damage or shear damage occur when stress condition satisfies the maximum tensile stress criteria or Moore-Coulomb criteria, respectively. And F1 and F2 are threshold function for tensile damage and shear damage, respectively. When computational elements satisfy the failure criteria, damage variable D is calculated by using principal strain, such this equation. And then elastic modulus of damage element decreases with damage evolution, according to this equation. And in this study, damage area where satisfied the failure criteria is regarded as fracture area. And in developed model, heterogeneity of mechanical property is also incorporated. Some mechanical property, such as elastic modulus and each strength in calculation domain, are distributed based on the Weibull statistical distribution. Okay, next, I explain the governing equation for fluid-driven transport within porous rock. Among these transport process, only for the groundwater flow and reactive transport are depicted in here. Groundwater flow within porous rock is calculated by conservation of water mass based on poroelastic theory and Gaussian flow. And permeability within fracture zone is calculated by using fracture aperture, such this equation. And reactive transport in pore water is calculated by basic advection and diffusion equation. And in this study, mineral reaction includes the mineral dissolution and precipitation on free surface in rock fracture, namely free phase dissolution, precipitation, and mineral dissolution at asperity contact in rock fracture, namely pressure dissolution. Therefore, the rate of mineral reaction R is expressed by both of reaction rate. And RFF represents the rate of free phase dissolution and precipitation of rock mineral, and RPS represents the rate of pressure dissolution of mineral. In this slide, the equation for pressure dissolution within generated fracture is introduced. In this study, damaged area is regarded as fracture area. So, pressure solution at fracture contact occurring only for damaged area where satisfies the failure criteria of tensile and shear mode. By depending failure mode of fracture, driving force component of pressure solution should be different as shown in this figure. By considering these aspects, change rate of fracture aperture due to pressure solution is defined by using tension and shear mode failure criteria given us this equation. And in the model, fracture aperture is changed by fracturing and subsequent occurrence of mineral reaction, such as free phase dissolution and precipitation and pressure dissolution. Therefore, fracture aperture at arbitrary time is formulated by such equation. In this equation, BD represents fracture aperture created by fracturing, And dot BPS represents the change rate of fracture aperture due to pressure solution introduced in previous slide. And as shown in this figure, when pressure solution progresses at asperity contact, fracture aperture decreases with time as well as permeability. And according to decrease of fracture aperture, asperity contact area increase. This relationship between fracture aperture and asperity contact area is represented by this equation. In this equation, RC represents fracture contact area ratio, which means the ratio of contact area to cross-sectional area of target fracture. Okay, next I'd like to present an example of numerical analysis by using the development model. In this analysis, development model was applied to predict long-term permeability change of bedrock around high-level radioactive waste within geological disposal facility. In this numerical analysis, subsurface environment was modeled by referring to deep underground condition in Porous area of Hokkaido, Japan. And actual field data was obtained from related literature. Analysis domain is shown in this figure. It represents the bedrock from depth 325 meter to 375 meter from Earth's surface. And that has a disposal cavity with diameter for 2.0 meter and the depth at 350 meter. And target rock is silicic mudstone. And in this analysis, at the first, analysis of cavity excavation was conducted. Secondly, by setting the result obtained from excavation analysis as initial condition, long-term coupled THMC analysis was conducted. Calculation period of long-term analysis is 100 years after disposing waste package into disposal cavity. And this analysis, it is assumed that target rock is composed of these 6 minerals. Each mineral composition is shown here. In excavation analysis, confining stress of 5.04 megapascal and 4.81 megapascal were imposed at top and side boundary, respectively, as shown in this figure. These initial stress conditions were estimated based on the result hydraulic fracturing test conducted at target site. And to simulate actual excavation process, firstly, internal outward radial pressure applied to cavity boundary to replace the in-situ stress condition was evaluated. And then it decreased monotonically by 1% per step for 100. In long-term analysis, physical property of bedrock updated by fracture generation during excavation analysis was set as initial condition. And then long-term coupled THMC analysis was conducted. In addition, heat radiation from waste package was considered by setting such time-dependent temperature history at the cavity boundary as boundary condition. From here, I'll introduce the numerical analysis result. At first, behavior of fracture generation during excavation analysis is shown in this figure. In this figure, blue-colored area represents the tensile damage, and red-colored area represents the shear damage. It is apparent from figure, fracture was generated around the cavity as excavation step progresses, and shear fracture was more remarkable than tensile one. This is animation of the fracture evolution. You can see the gradual crack propagation with excavation steps. Next, I explain the long-term permeability change. These two figures represents the change of permeability distribution around the cavity in two different cases. PS condition cases that are considered a full THMC process that includes a pressure solution. No PS condition case doesn't consider pressure solution. And in this figure, permeability is shown by log notation of log 10K. And from this figure, in initial state, permeability in damaged zone increased by about 2 orders of magnitude greater than undamaged intact zone. And this figure shows that permeability is almost unchanged with time under the no PS condition case. In contrast, under the PS condition case, permeability in almost all the damaged zone eventually decreased by 1 order of magnitude after disposal of radioactive waste. This permeability reduction is because the fracture sealing by pressure solution occur in damaged zone. This is animation of fracture permeability evolution. You can see that the permeability in damaged zone decrease with time due to pressure solution. Next, in order to more quantitatively examine the permeability evolution, change of permeability at specific point are observed. This figure shows observation point in damaged zone. And this figure shows the permeability change at observation point under no PS condition and the PS condition as shown in this figure. It is apparent from this figure, permeability significantly decreased in early stage of analysis period due to pressure solution. For investigating permeability reduction confirmed in this figure, permeability change within first 10 years are shown in this figure. This figure shows that permeability decreased by about 1 order of magnitude within 5 years. And afterwards, permeability approaches the convergence value. Finally, conclusion. In this study, we develop a new coupled THMC model that can consider both fracture generation and subsequent occurrence of mineral reaction, such as pressure solution in rock fracture. And then, by using a developed model, we conducted prediction of long-term behavior of natural barrier. Obtained analysis results shows that many fractures occur near disposal cavity and permeability increase in cracked zone during the cavity excavation. But after excavation, permeability cracked zone decreases with time due to geochemical creep by pressure solution within fractures. These results indicate that pressure solution within fractures may have non-negligible impact on reducing hydraulic damage of natural barrier. Okay, thank you for kind attention.
Thank you very much, Dr. Ogata, for your very interesting presentation. So now we have 10 minutes for the Q&A session. So does anyone have any questions from the audience? So if so, please use chat or the raise hand feature in Zoom. Do you have any questions?
Sorry, I don't know what is the raise the hand feature in Zoom because I didn't have any experience.
Okay, you
doing
have the
that.
react. I think you
Can
have
I
the
start,
reaction. Yeah, if you have any question, you can. Yeah, you
Yeah,
can.
yeah, thank you.
Yeah, please ask.
So my question is that can you introduce which kind of programming language did you use for making this your own algorithm and showing a visualize? Okay, MATLAB and
Okay. Yes, this code is composed of the COMSOL multiphysics, COMSOL multiphysics FEM. This is a multiphysics FEM analysis code, commercial software, and geochemical code of Flux. We combined these two numerical tools linked by MATLAB language.
And is it a popular software that shown in the right below? PHR
Flux?
Yeah.
Yeah. Flux is popular for computing the complex geochemical calculation, geochemical reaction.
Thank you.
Okay, thank you very much.
Do you have any other questions from the audience? So you can just turn on your microphone and video if you don't know how to use the Zoom utility. Please feel free to ask.
Can I raise one more question?
Okay, of course.
In case of TM or HM coupled problems, I know that there are some well-known analytic solutions. So developers or some new numerical codes are very easy to verify. But in case of THMC coupled process, I think it's very complex. So it'd be very hard to find an exact solution, which can be used as a reference for verification. So can you explain some kind of strategy for verification of this code? Or, I mean, THMC in general?
Okay, thank you for question. Actually, as you said, verification for comprehensive THMC process is a little difficult by using analytical solution. So we have validated the coupled THMC model by comparison with experimental data conducted under the THMC coupled condition. For example, in this case is a flow-through experiment to single rock fracture under the coupled THMC condition, stress and temperature and water flow condition. In this case is our simulator reproduce experimental data well.
Okay, thank you.
Thank you.
Okay. I think we have still time for short questions, or do you have any questions? Okay, can I ask you one question? Okay, currently your THMC model is 2D based numerical simulation. So, but in actual rock mass, the fracturing happens in 3D manner. So, and I think that this makes and complicates your problem more, and it needs more development. So, is it so using 2D and do you think you can capture the real problem correctly, qualitatively and quantitatively? So, I mean, how can you validate? I mean, verification can be done using some like the benchmark problem for each component, but for the real validation, so how can you do that? I'm really interested in such validation process of this kind of very complex problem. I really need your answer. Thank you.
Okay, thank you for question. Yes, my numerical code is now the 2D code. But previously I compare the in-situ test, in-situ excavation test, 3D, in-situ 3D excavation test with analysis result of 2D code. By comparison, we can confirm that our 2D numerical codes can reproduce the real 3D excavation process and permeability change process. This result, the permeability change with time after excavation. Analysis result can capture the trend of the real 3D phenomenon by 2D numerical code. From this result, I think it is enough. It is enough to use 2D numerical code for predicting the permeability evolution during geological dispersal period.
Okay. Thank you very much. Yota, I think it's almost time, right? I think.
If there is time, can I ask a question?
Okay, of course. Please.
I understand the main application you are looking is the waste disposal, but what other applications do you see for this sort of modeling? And when do you think, the process is very complex? Is there, are you guys thinking about making it more applicable for day-to-day problems of engineering?
Yes, thank you for question. The other application is typical other applications. I think geothermal reservoir. In this application, the complex coupled problem similar to the geological disposal problem. I think our code will be able to apply the geothermal reservoir, and additional the application problem is carbon dioxide storage problem. Okay.
Okay, thank you very much. I think it's almost time, so yeah, please, Yota, please proceed.
Okay. Now let me introduce. Firstly,
okay. Thank you very much,
again, Dr. Ogata.
Okay. Sorry.
Yeah, please stop sharing your slide. Thank you very much.
Okay.
Now let's move on to the second presenter. The next presenter is Dr. Sehyeok Park, currently a senior researcher in Korea Institute of Geosciences and Mineral Resources. His research interests include hydromechanical behaviors of fractured rock, reservoir hydraulic stimulation, induced seismicity, in-situ stress estimation, and 3D geological modeling and geological disposal of radioactive waste. He earned his PhD in energy resources engineering at Seoul National University in 2021. During his graduate study, he participated in the research projects on geomechanics simulator development, enhanced geothermal site development, and Korea-Europe collaborative research on the demonstration of geothermal well stimulation. Today, he will present a talk entitled Comprehensive in-situ stress estimation for a fractured geothermal reservoir from drilling, hydraulic stimulations, and induced seismicity. Dr. Park, the screen is now yours.
Thank you, Dr. Hashimoto. I will share my screen now. Let's see. Can you see the screen in a full presentation mode?
Yes, I can.
Okay, thank you. So I will start. Hello, everyone. My name is Sehyeok Park from South Korea, and it is my great honor and joy to introduce my study in this seminar. And I sincerely appreciate to have this opportunity to introduce my study. My talk is about estimating the in-situ stress condition of the Puang geothermal reservoir in Korea using various types of direct and indirect stress indicators. And I'd like to acknowledge that this is based on my doctoral dissertation that I finished last year. Let me introduce the Puang geothermal project first. So the project was started at the Puang city, located at the southeastern part of Korea. Two wells called PX1 and PX2 were drilled deeper than 4 kilometers at the site, and 5 hydraulic stimulations were conducted during 2016 and 17 to make an artificial geothermal reservoir. But 2 months after the last stimulation, the magnitude 5.4 earthquake occurred at the site on November 15th, 2017. After the earthquake, the Korean government appointed an investigation commission. And after years of their work, they concluded that the earthquake was triggered by the effects of seismic events induced by the hydraulic stimulations and geothermal activities at the site. Similar to any other geomechanical behaviors, the hydraulic stimulation and induced seismicity are strongly affected by the stress condition of the rock mass of our interest. There were a few previously suggested stress models for the Puang site, but as you can see from this slide, these stress models disagreed each other in terms of both stress magnitudes and also stress orientations. I thought that we need to continue more study and discussion on the stress model of the site. And in this regard, this study focused on suggesting a stress model of the Puang site that best explains various field observations and also the occurrence of the Puang earthquake. From this slide, I will explain the stress indicators that I collected for stress integration in my study. For comprehensive stress estimation, the stress indicators were collected from various field observations, and in PX1 well, lost circulation occurred at 4.1 kilometer depths and under the mud overpressure of 14 megapascal. And during the followed stimulation at the PX1 well, clear pressure peaks were observed at well pressure 15 to 17 megapascal. So those signals indicate that same fracture was opened at consistent pressure levels, and compared to PX2 well, the pressure peaks were about 50 megapascal lower than that of PX2. So which means that PX1 and PX2 had clearly distinct stimulation mechanisms. So overall, these observations indicate that there were hydraulic shearing in PX1 occurred by a head pressure of 14 to 15 megapascal. In PX2 well, considerable amount of lost circulation occurred at 3.8 kilometer depth. The government commission reported that this lost circulation was through the fault on which the magnitude 5.4 earthquake occurred, and seismic events continued for a month since the start of lost circulation. So these seismic observations imply that the fault was sheared by the pressure of drilling mud. There is another vertical well at the site, which is actually a closed vertical section of PX1, so called as PX1V. Interesting point here is that there was no lost circulation while drilling the same depths in PX1V. So the graph here shows the difference of bottom of flowing mud pressure in PX2 and PX1V. at the same depth of px2 loss circulation. So it means that this 50 to 66 megapascal bottom of pressure range is the pressure window to shear the main shaft faults at px2 3.8 kilometer depth. There were also important observations during the stimulations at the px2. When a fracture is opened by fluid injection and closed during the shut-in period, a very unique pressure signal is observed at the moment when fracture faces are closed. And this so-called as fracture closure pressure is regarded as the normal stress acting on the fracture. And as no packers were used during stimulations, fractures with various orientations were exposed to water pressure. And the fracture with the lowest normal stress would have produced the most dominant pressure signal. So in this regard, the fracture closure pressure in px2 shown here can be interpreted as the minimum principal stress at the target depth. The seismicity data also provides information on in-situ stress. Focal mechanism of an earthquake contains the information of fault plane orientation and also the slip movement direction. So by using stress inversion of focal mechanisms, we can obtain the stress orientation and stress ratio that best explains multiple fault slip movements. The table here shows various stress inversion results for the Puang site. Interestingly, we can find that the results largely agree on the strike slip faulting regime and the stress ratio of about 0.87 to 0.89. The next stress indicator was obtained from the caliper logs. Boho wall failure is frequently found from a well in a high horizontal stress condition. In Pohang px2 well, both Boho breakout and washout are found from multiple sections of its forearm caliper log data. In oil and gas industry, it is empirically known that the Boho breakout, initially wider than 90 degree, will grow in its width and could possibly transform into Boho washout. So from this empirical criteria and the observation from px2, an assumption was made that the stress condition in the Puang reservoir is in a range, making the initial breakout width to be about 90 degrees. So from this page, I will explain how the field observations were integrated into to suggest a matching stress model. A conventional stress polygon is a diagram showing the possible range of maximum horizontal and minimum horizontal stresses defined by Moore-Coulomb shear criteria under a given single vertical stress. However, in this study, stress indicators were collected from many different depths, so those could not be compared on a single stress polygon for a single vertical stress. Because of this, I adopted the concept of normalized stress polygon, so which is using horizontal over vertical stress ratios as the x and y axis instead of just horizontal stress. So by doing this, a single normalized stress polygon can cover multiple depth ranges. So it is convenient to compare the stress indicators collected from multiple different depths. Let's call the fluid pressure to shear a given fracture as the critical fluid pressure, PC. The PC can be analytically calculated, so we can easily show the stress conditions to allow hydraulic shearing in px2 fault or in px1 fracture or fault. So to draw contour of PC on stress polygons, the orientation of the main shaft fault plane was adapted for px2 shearing, and 4 different fracture plane orientation scenarios were set up for px1. And what you can see from here, the stress ranges shown on the stress polygons for specific stress azimuths and friction coefficients scenarios. Sorry, I think I have a problem in my presentation file, so maybe I should pause my presentation here for a moment.
Can you share the screen again?
Okay, wait a second.
Yes. Now
Can
I
you see the
see.
screen?
Yes.
Okay, sorry. So I'll continue my presentation. So the next stress indicators are shown here. The fracture closure pressure in PX2 and the focal mechanism stress inversion results are shown on the same stress polygon. These two stress indicators does not change with stress orientation or friction coefficient. And also they are very narrow on the stress polygon, so very helpful to pinpoint the matching stress condition. So as you can see, the stress ratio from stress inversion are shown in gray shaded area, and fracture closure pressure is shown in orange. So this narrow area are crossing both of the stress indicators are very helpful to narrow down the possible stress range. What is shown in pink dot and gray line here is the extension of acoustic emission test results of the rock cores that we sampled from 4.2 kilometer depth of PX2 well. Although it was only used as subsidiary indicator in this study, it locates very closely to the region where the stress indicators of focal mechanism inversion and also fracture closure pressure cross each other. Sorry, I have the same problem now, so maybe I should restart my PPT file. As mentioned earlier, both breakouts and washouts were all observed in PX2, and I assumed from that the stress condition would be a range that defined the Boho breakout initial risk to be about 90 degrees. So the equation here shows the horizontal stress relation for a given breakout risk. So using this equation, it is possible to show the stress condition to make initial breakout width to be between 80 to 100 degrees. And the result is shown in green shade on the right figure here. Integrated stress estimation in this study was performed by combining all these stress indicators on the same normalized stress polygon. Figure on the right is an example that all 5 major stress indicators overlap at the same region shown with blue dashed lines. So this is an example case at a specific friction coefficient and stress orientation. And some of the stress indicators change with these conditions. So similar combinations were tried over many different conditions. Sorry, I'll share my screen again. I think it'll be better to present in this screen mode. So what you can see from here is an animation showing that as the friction coefficient and stress orientation changes, the stress indicators change and it makes different conditions for their overlap. So by performing several scenarios based on friction coefficients and stress orientation, and also the fracture orientation for PX1 shearing, I resulted the stress estimated results in here for stress ratios, vertical, minimum horizontal, and maximum horizontal stress ratios, and also the possible range of friction coefficients to match all those stress indicators in the same region. Next one is the refinement of stress orientation and friction coefficients based on the stress magnitude and orientation determined in the previous step. So what is shown in here are some reference planes from focal mechanism of foreshocks and main shock occurred on the same day of November 15th, 2017. So by using those plane orientations and slip movement direction, we can calculate some theoretical seismic theoretical slip direction, and we can compare its direction with the actual direction measured by focal mechanism. And what you can see as the colored solid and dotted lines in here are the angular distance between the actual measured slip vector orientation and also the calculated slip vector orientation. And red dashed line here is showing the root mean square of these 8 candidate fault planes. And what we can see here is that at the stress, maximum horizontal stress orientation of about 101 to 110 degree, or at 106 degree, the root mean square is minimized. So we can determine or narrow down the possible range of stress orientation by using this kind of method. And what is shown below here is the slip tendency. And we can see that at the determined stress orientation, the only possible range of friction coefficient is about 0.35 to 3.8, because any friction coefficient bigger than 0.4 will not match the slip tendency of these 8 candidate fault plane orientations. The next step, I demonstrated the slip tendency of these 8 candidate fault planes using the determined stress magnitudes, orientations, and also the suggested range of friction coefficients. So what you can see from here is the stress slip tendency contour on a stereo net. And what is shown here is the more circles with 8 different fault candidate plane orientations. And these triangular markers are from foreshocks. So what we can say is that these four shocks have very high slip tendency, almost critically stressed close to the failure criteria. So assuming that those four shocks occurred on the same day with the main shock could possibly trigger the main shock, I think examining the possibility of the criticality of those four shocks are more important than the criticality of the main shock. So this kind of Moore circle can decently demonstrate such possibility of critically stressed states at the moment of four shock occurrence. So this is the conclusion based on many different stress indicators observed in the PX2 and PX1 wells at the site, and also the lab test results. I combined all those direct and indirect stress indicators in a stress polygon to deduce a decent stress model that best explains all the observations and also the seismicities. I mean, four shocks and main shock occurred on the same day of the 5.4 event. And this is the resulting stress model. And I decided to determine the stress magnitudes and orientations and the possible range of friction coefficients. And this is the figure showing the comparison of the newly suggested stress model in this study and the other stress models of the previous one. And from the suggested stress model, the slip tendency of the possible candidate fault planes of the four shocks and main shock on November 15 is about 96 to 98% of critical level. So that's all I prepared for today's presentation. And thank you all for listening to my presentation. Thank you.
Okay, thank you very much, Dr. Park, for your very interesting presentation. Now we have 10 minutes for the question and answer session. So if you have any questions, please turn on your microphone and or you can also use the raise hand feature of the Zoom. Is there any question or comment? Okay, let me ask a question from me, and I wonder what would be the reason that makes your new stress model to be very different from the previous suggested one?
Thank you for your question. I think we should address the stress models, the previously suggested stress models first. So what you can see from here are the summary of those stress models. This very sharp diamond is the newly suggested model, and the other four are previous ones. And the important thing is that for the same depth of 4.2 kilometers, there were two different previously suggested models. One is by Kim 2017, this blue dot, and the other one was by the government commission. And I think the main difference between the government commission's model and my stress model comes from first from the interpretation of the hydraulic stimulation data. As I introduced for the fracture closure pressure here, I determined the minimum horizontal stress, minimum principal stress as 60 megapascal from this fracture closure pressure data, but it was not included in the government commission's study. So I would say using this fracture closure pressure for as an indicator of a minimum horizontal stress was first suggested in my study. And in case of the government commission's work, they suggested that the minimum principal stress was the vertical and intermediate was the minimum horizontal stress. So in turn, they resulted a different stress regime. So where's the conclusion? This one. Yeah, so as you can see from this stress polygon, this left top triangle is for strike slip faulting regime, and this right one is for reverse faulting. And only government commission's result is located on reverse faulting because they determined the vertical stress to be minimum and intermediate to be minimum horizontal stress. So that's the main difference of interpreting hydraulic stimulation. And the second one is about assuming the critical stress state. So from this animation that I showed, I determined the matching stress region by combining multiple different stress indicators, and it resulted friction coefficient which is quite lower than a typical range known as Byerlee slope, which means that friction coefficient of typical rocks are ranging from about 0.6 to 0.8. But from this combination, we can only deduce friction coefficients as low as around 0.3 to 4. So this much difference of friction coefficients results in a huge difference. So that was the second important region.
Okay, thank you so much for the additional information. Is there any other questions or comments?
I have one question. So going forward, with, what do you think that they would have done differently to avoid this happening?
You mean the earthquake?
That's right. Yeah. Obviously, there is going to be more fracturing in the future. And what are the learnings of these studies that can be used in the future to avoid something similar happening?
Although this study is not focused on the induced seismicity mechanism itself, but I think this Puang event was very unprecedented event, and in terms of relation between injected volume and earthquake magnitude, it was very different from the other induced seismicities before Puang. So because of that, as I know, this Pohan case is raising many following researches about the mechanism of induced seismicity and also the prediction of the seismicity magnitudes from operational features. So I think it would be, I think there could be some possible options that we should consider to prevent further unprecedented occurrence of large earthquake from hydraulic injection. Would be fault mapping, a geological exploration of fault structures, and screening out some possible risky structures. And also we have to put more keen interest about the frictional characteristics of those fault structures. And also, as I know, there are some multiple studies ranging the topics about more advanced traffic light system that is agreeing that we can manipulate the occurrence or control the induced seismicity magnitude by well operating the injection scheme. So I think it is also a very interesting topic to further deepen this topic into for more nice development of in-situ geothermal system technology.
Okay, thank you for the discussion. And is there any other comments from the floor? If there is no question, I'd like to end the second presentation. Thank you again, Dr. Park.
Thank you.
And now we are at the end of the second ISRM Young Members Seminar. On behalf of, just a moment. Okay, thank you, Dr. Fukuda. Now, on behalf of the organizing committee, I'd like to thank the ISRM for helping us in the organization of this event. I would like to thank Dr. Ogata and Dr. Park for their very interesting and valuable presentations that addressed two relevant topics of rock mechanics. We hope that this seminar provides you new insights and new challenges for future research, and it could be a periodic event for sharing ideas about rock mechanics and related topics. For this reason, we want to invite you for the next seminar that will be virtually hosted by Latin America on March 30th. In the next seminar, Dr. Chimie Suzuki from University of Chile and Dr. Alexander Ramos from the San Vicente mine in Peru will present their works respectively on numerical modeling of rock masses in block cave mining and strategy and tactics for burst-prone conditions in underground mining. Further information on this event will be available on ISRM newsletter and website, so keep in touch not to lose the next webinar. In addition, if you are interested to participate, contact us at ISRM via this email address of the organizing committee. Finally, thank you for your participation and have a good day and safe day.
Thank you very much.